This next section is about finding Taylor or Maclaurin series for a function. The big difference now is that we're talking about a series, not a polynomial. So we are going to talk about some infinite series, and we're actually going to look at some common infinite series that are important ones for using for building blocks. So the first important one is the geometric series. So we're going to look at this function, and we're going to find the Maclaurin series for this function. Using the same process we used before, so if Maclaurin series is centered at 0 because it's Maclaurin. Remember, they don't have to tell you it's centered at 0. And so we're going to have f of x and f prime of x. We'll have to use the chain rule when we take this derivative, so it'll be negative 1 minus x to the negative 2 times negative 1. Which will just be 1 minus x to the negative 2. And it's a series, which means it goes on forever. We have to take enough derivatives that we will see a pattern so that we can write our nth term. We might not get there on the first go, and if we don't, we'll just have to do it again. I'm just hoping that we'll see a pattern as we work. I'm already seeing that this chain rule is going to cancel out the fact that we're bringing down a negative exponent. We're bringing down this negative 3, it becomes negative 6, but then we would multiply by a negative 1, so this will just be positive 6. Okay, I'm going to stop there and see if that's enough. So then it's Maclaurin, so we want to evaluate all of these at 0. And then we're going to write our polynomial. So p of x is 1 plus x plus 2 x squared divided by 2 factorial, so these cancel, and then 6x cubed divided by 3 factorial, so these cancel, and so I think what's going to happen is that all of our factorials and our derivatives are going to wind up canceling, so our power series is just 1 plus x squared plus x cubed, etc., all the way until we get to x to the n, and then forever. So this is our Maclaurin series. We're going to start at n equals 0, and we're going to go to infinity, and we would have x to the n power. And this series is geometric because each term is multiplied by x. So this series is a geometric series, which means that the sum would be a over 1 minus r. Well, a is 1, and r is x, so look at that. That's what we were trying to find. And then the other thing is that this is true, but not true for all x's. It's only true on the interval where the absolute value of r is less than 1, or since r is x, when x is between negative 1 and 1. So that's our interval of convergence, and we don't even have to check the endpoints because we know that our series would not converge at those endpoints because it would still be geometric, but we wouldn't be multiplying by a number less than 1. So that is the Maclaurin series. So this is kind of our answer right here. This is the Maclaurin series for that geometric series. And this is actually one that's worth knowing. And one of the things that's worth knowing is kind of that format, a over 1 minus r. Here's an example of another one that maybe right away you can say, hey, maybe that's geometric. And if it's geometric, I can say 8 plus 1 over 1 plus 2x cubed. And I can set that equal to a over 1 minus r. And I can say, well, then 8 would be a, and 1 minus r would be 1 plus 2x cubed, so r would be negative 2x cubed. So then my series would be 8 plus 8 times negative 2x cubed to the 1 plus 8 times negative 2x cubed squared. And we're not doing the Taylor series now because we're doing a geometric, we're making just a geometric series, noticing that this is geometric. And so if I wrote my general term, it would be 8 times negative 2 to the n times x to the 3n. And so that would be my geometric series, and I don't need to go through the whole process of creating the series using derivatives because I recognize this as fitting the geometric pattern. So one of the big ideas is we can find the Maclaurin-Taylor series for a simpler function and use algebraic properties to find a series for a more complicated function, so that 1 over 1 minus r was a simpler 1 minus x is a simple function, and it extends to, we can recognize that this is now going to work anytime we have something that fits that geometric pattern. All right, this is the first part of this unit. You can move on to the next video. Thank you.